Length Contraction by Kimia, Alex, Ben, and Theo.
Recall that time dilation is the slowing down of time in one reference frame moving relative to an observer in another reference frame. This is important to know as time dilation and length contraction go hand in hand with each other. How does time dilation cause length contraction? Good question, but you're getting ahead of yourself.
But first, what is length contraction? Length contraction is the shortening of a distance in an inertial frame of reference moving relative to an observer in another inertial frame of reference.
Let's say that you are traveling at 90% light speed relative to a stationary observer. Because of time dilation, you would experience time moving by slower than the observer.
However, both you and the observer would agree on your velocity. Since distance is equal to velocity multiplied by time, and the time is shorter for the person traveling at 90% the speed of light, while the velocity remains the same from both perspectives, the distance traveled by the person moving faster would appear to be shorter. This shorter distance is known as the relativistic length.
Muons are elementary particles whose decay demonstrates how time dilation and length contraction complement each other. A muon is a subatomic particle that is about 200 times as massive as an electron and travels at 99% the speed of light. Muons decay in 2.2 milliseconds for an observer at rest relative to the muons, meaning that if you're traveling at the speed of a muon observing a muon, it would decay in 2.2 milliseconds.
Muons are produced by cosmic radiation colliding with atoms in the Earth's upper atmosphere. Due to their velocity and their decay period, it is expected that the muons would make it 660 meters into the Earth's atmosphere before decaying. However, experimental evidence shows that most of the muons decay after traveling about 4,800 meters into the atmosphere.
Why do the muons decay so much later than expected? In short, special relativity. As observed from the Earth, these muons undergo length contraction. From the muon's point of view, it is traveling for a certain amount of time at 99% of the speed of light. However, due to time dilation, time moves more slowly for them, and the time around them moves faster. That means that a muon only sees itself move around 660 meters before decaying, but it actually moves around 4,800 meters from the point of view of a stationary observer on Earth.
The muons are proof that length contraction exists, but according to special relativity, length contraction shouldn't exist. This contradiction is called the twin paradox, and it works like this. Let's say that you have a twin who is leaving Earth on a spaceship traveling near light speeds. Time dilation would make it so that the person moving would experience time more slowly. However, the paradox is that both frames of reference exist.
The first understanding of the scenario is from the point of view of the person on Earth. In this frame of reference, the spaceship is moving away, and as such, when the twin on the spaceship returns, they would be younger because the time moves slower than in motion, as per this equation.
However, from the perspective of the twin on the spaceship, they are at rest, and as such, the entire universe, including the twin back on Earth, is moving. Consequently, the twin back on Earth would experience time slower, as per the equation. These 2 points of view are contradictory to each other, so which one is right? Well, as it turns out, the twin on the spaceship would be younger when they return. So why is one frame of reference correct while the other is not, when in almost every other case, both frames of reference are acceptable?
The answer is that the one who experiences acceleration is the one who is moving for the purposes of time dilation. And since the person on Earth does not experience the force of acceleration due to the rocket ship moving, it is accepted that they are the ones at rest.